Hi everyone, I hope we're all well, and welcome to the third lesson in National 5 Computing Science Computer Systems unit. Today what we're going to look at is ASCII representation of text. Okay, so we've already had a look at how computer systems store numbers, how we convert binary into denary and vice versa, and how the computer utilizes floating point representation. So today what we're going to look at is how text is stored in computer systems. So the way we do it is by using what's known as extended ASCII code. ASCII stands for American Standard Code for Information Interchange, and it's the standard way of representing text in a computer system. ASCII uses 8 bits or 1 byte to represent every character on the keyboard. This gives us 2 to the power of 8, which is equivalent to 256 different values. This is more than enough to represent upper and lowercase letters, the digits 0 to 9, all punctuation marks and symbols, and even the control characters on the keyboard that don't appear on the screen. So control or non-printable characters occupy the first 32 elements out of the 256 available. But it's important to remember that this number between 0 and 255 will be stored in the computer as a binary number. So any key on the keyboard will have a number attached to it, and that number will then be stored in the computer system as a binary number and not the denary number that you'll see later on. So if we have a look at some examples of printable characters, so they're all of your lowercase and uppercase letters, your digits and the symbols. They're anything that if you type on the keyboard you will see appear on the screen. Okay, so they're printable. Non-printable or control character examples, so Shift, Alt, Delete, Tab, Backspace or Return. They are characters that when pressed will manipulate the text, but it won't actually print anything onto the screen, and that's why we call them non-printable or control characters. So here's an example of an ASCII table. Okay, so if we have a look, you can see the number 0 to 255, so there's our 256 characters. Okay, it's plenty to store all of our symbols, our lowercase, uppercase numbers, or letters and numbers. So if we have a quick look at, say for example, 33, okay, so it's the second column in towards the top, you can see that the number 33 represents an exclamation mark. How does the computer store this though? Well, we can see that the exclamation mark is equivalent to the denary number 33, and therefore we would store it in binary as 001 00001, because that binary number, 8-bit binary number, equates to 33 in denary. So what's important to do, especially at Nat 5 here, is to understand how we calculate the storage requirements of any piece of text in a computer system. Okay, because extended ASCII uses 8 bits or 1 byte per character, this means that every character in a string will require 1 byte of storage. This includes every letter, every space, which is really important to remember, every symbol and every number. Okay, so if we have a look at the example below, if we have hello exclamation mark, that's 6 characters and therefore will require 6 bytes of storage in the computer system. If we have the words extended ASCII code, that has 19 characters, because remember we have to count up the letters but also the spaces. That will then require 19 bytes of storage. There are only 10 types of people in the world, those who understand binary and those who don't. 97 characters, including all spaces, therefore 97 bytes. If you can work out this joke, let me know in the comments when you submit your work as well. So that's everything that we need to know for task sheet 3. Okay, so it's called Data Representation 3 ASCII. Okay, I'll attach it to this notification. Just use the task sheet itself. I've put all the theory on there that should help you understand and answer all of the questions. Also use this video, but also if you need, you can reach out and ask for further help. Okay. Okay, good luck.